Hey YouTube, my name is Krishna Suri, and I'm starting this new channel called Biology Without the BS. And my goal is to make science and other science-related topics as easy for you as possible. And just as my motto states, it's going to be science simplified. So I found a topic that often challenges a lot of students from classes anywhere from general biology to organ physiology to neurobiology, is the concept of action potential. So as kind of a quick review, I am going to walk through an action potential graph and explain what occurs at each point in the graph. Now, let's begin our walkthrough and let's go through the sequence of events. Now, if any of you guys are football fans, you guys probably saw Monday Night Football last night, and you saw the ridiculous set that Ndamukong Suh put on Jay Cutler. Now, think about it. As Ndamukong Suh's elbow was pushing Jay Cutler's face to the ground, he probably activated some kind of mechanoreceptors in Jay Cutler's face. So these mechanoreceptors, they sense the vibrations of the ground, and they open sodium channels. So, let's take a look how the opening of those sodium channels affects the voltage across the membrane, in addition to ultimately affecting chemical and electrical signaling. And so the concept of action potentials is based on changes in the electrical and chemical gradients of ions. And so each ion has its own electrochemical gradient. And each ion has its own equilibrium point. And so the equilibrium potential of an ion is a point at which there's no net movement of ions across the membrane. So when you have a membrane charged at plus 60 millivolts, you have no net movement of sodium ions. So at 60 millivolts, there would be no movement of sodium ions. But there would still be movement of other ions that have not yet reached their potential. Okay, so the resting membrane potential is a kind of a conglomerate of all these factors. It includes temperature, the concentrations, the relative concentrations of ions inside and outside the membrane, in addition to the relative permeability of each of these ions. And the permeability of these ions is influenced both by its natural characteristics, such as polarity. Like, for example, you can imagine an ion, like a cation, such as sodium. It's very charged because it's an ion. So if it tries to go through the very hydrophobic layer of the membrane, it can't pass. Because you see, remember, like dissolves like. Also, the relative permeabilities of ions are influenced by integral membrane proteins, because these proteins can help move the ions in and out of the cell regardless of their charge or their chemical gradient.